Hi there, I'm Rebecca Weaver. We're looking at section 7.4 today, Lagrangian multipliers and constrained optimization. So, the method of Lagrangian multipliers. In this section, we're going to optimize an objective equation, f of xy, given a constraint equation, g of xy. However, the methods of chapter 2 will not work, so we must do something different. Therefore, we must use the following equation and theorem. F of xy lambda equals f of xy plus lambda times g of xy. So here's our theorem. Suppose that subject to the constraint g of xy equals 0, the function f of xy has a relative maximum or minimum at xy equal ab. Then there is a value of lambda, say lambda equals c, such that the partial derivatives of f of xy lambda all equals 0 at xy lambda equal abc. So here's our steps for Lagrangian multipliers. We're going to solve L1 and L2 for lambda in terms of x and y, then equate the resulting expressions for lambda. We kind of did a little bit of that last time in finding those partials and equating and finding y. So solve the resulting equation for one of the variables. Substitute the result of step 2 into the equation L3 and solve the resulting equations of one variable. Use the known variable and the equations of step 1 and 2 to determine the other two variables. So our L1 is going to be the partial of f with respect to x equal to 0. L2 is going to be the partial of f with respect to y equal to 0. And L3 is going to be the partial of f with respect to lambda equals 0. So this sounds very confusing, but follow these steps and it'll all work out. So we're going to maximize the function x squared plus y squared, subject to the constraint 2x plus y minus 3 equals 0. So we have f of xy equals x squared plus y squared, g of xy equals 2x plus y minus 3, and f of xy lambda equals x squared plus y squared plus lambda times that g function, which is 2x plus y minus 3. So we need to write that down. Now, let's look at our equations L1 to L3. So for this case, we have the partial of f with respect to x is just going to be 2x plus 2 lambda equals 0. The partial of f with respect to y is going to be 2x plus lambda equals 0. The partial of f with respect to lambda is going to be 2x plus y minus 3 equals 0. From the first two equations, we see that lambda equals negative x, which is equal to negative 2y. So let's write x equals 2y. Then we're going to substitute this expression for x into the third equation, and we're going to derive 2x plus y minus 3 equals 0. So plugging in that value 2y for x, we're going to solve that for y, and we're going to get that y is 3/5. Now using y equals 3/5, we find that x is going to be equal to 6/5. Lambda is going to be equal to negative 6/5, plugging that into both those two equations. So the maximum value of x squared plus y squared with x and y subject to the constraints occurs when x equals 6/5, y equals 3/5, and lambda equals negative 6/5. That maximum value is then going to be, plugging that in to my x squared plus y squared, is going to be 1.8. Just follow the steps. Now, let's look at a word problem where we have to come up with our equations here. $480 are available to fence in a rectangular garden. The fencing for the north and the south sides of the garden costs about $10 a foot, and the fencing for the east and west side costs about $15 a foot. Find the dimensions of the largest possible garden. So we're going to let x represent the length of the garden on the north and south sides. Y is going to represent the east and west sides. Got to call it something. So we want to use all $480. So we know that 10x plus 10x plus 15y plus 15y equals 480. We're going to simplify this constraint equation so that we have g of x, y equals 20x plus 30y minus 480 equals 0. So there's our g. So we must now determine the objective function. We wish to maximize our area, so our objective function should be about the quantity area. So the area of the rectangular garden is xy. Therefore, our objective equation, area, equals f of xy, which is just x times y. Therefore, f of xy lambda is going to be equal to f of xy plus lambda times g of xy. So that's going to give us xy plus lambda times that g that we found, which is 20x plus 30y minus 480. Now, once you have this, that was a hard part. Now you're just going to follow the steps. You're just going to calculate L1, L2, L3. We need the partial of f with respect to x. We need the partial of f with respect to y. We need the partial of f with respect to lambda. So taking those partials, L1 is going to be y plus 20 lambda equals 0. L2 is going to be x plus 30 lambda equals 0. And L3 is going to be 20x plus 30y minus 480 equals 0. Okay, from the first two equations, we see that lambda equals negative y over 20 equals negative x over 30. Solving this for y, we have y equals 2/3 x. Substituting this into our third expression for y, we're going to get 20x plus 30y minus 480, plugging that in, solving for x, we are going to get that x is 12. Now using x is 12, we're going to find that y is equal to 8 and lambda equals negative 2/5. So the maximum value of xy with x and y subject to the constraint occurs when x is 12, y is 8, and lambda is negative 2/5. The maximum value, 96 square feet. And this concludes section 7.4. If you have any questions, you be sure and email me, rweaver10@alaska.edu, and have a fantastic day. Thank you.